It's nice to see you all again this evening, and I want to take a few minutes to take you one more step, if that's all right. You and your DNA. Except for those who are here for the first time this evening, I think that would look somewhat familiar. That ladder is untwisted so we can kind of see it. It represents the DNA. And why are there four colors? Because there's four different kinds of half rungs, isn't there? And always the half rungs that are marked A hooked to T's. I think you can barely see that. There's a T hooked to an A, and somewhere along in here, I can hardly read it where I'm standing from. But in any case, what I want to illustrate this evening is something that we actually knew part of this 40 years ago. But it wasn't until the genome was sequenced that this whole thing just came home to everybody. And let me show you what it is. Let's just say that this, from one place on the DNA ladder to another place, is the gene. And just to review, genes code for building what? Proteins. That's what they do, nothing else. And proteins run the show. The proteins that the genes make can protect you from cancer, right? Those are the ones that, the inhibitory or tumor suppressors, we call them. The tumor suppressor genes. The gene doesn't suppress the tumor. The gene makes a protein that corrects the mistakes on the DNA so the cell doesn't become cancerous. That's the kind of mechanism. There's probably other mechanisms that we don't fully understand. Now here's what, if you will, blew away the scientists when it finally dawned on them what was going on. Instead of a copy being made, like I showed you yesterday, there's the copy. You may remember that the DNA gets opened, a little machine comes in and makes this half copy along here, and the half copy is pulled away and taken to the protein manufacturing factory, correct? You remember that? Here's what actually goes on instead. The RNA, if you're with me still, this copy portion that's going to go to the factory, the RNA is cut up into pieces. And I'm just going to show you the pieces with these colored bars. These bars aren't there. I'm just putting them there so you can picture that the pieces that are marked in yellow are eliminated. We have a name for them. I hesitate to always give you the names. It's not important. But scientists have named those introns, something that stays in, whatever. And then these three pieces are glued together, if you will, to become the RNA that actually is used to form the protein. And so those are the three blue pieces, if that makes sense for you. And by mixing and matching these, you see they're not necessarily taken in the same order. You could have the bottom one put in the middle. Would that be a different protein then? It would be, because the order of the amino acids would be different. And I'm just showing you that when you have three segments that you're going to use to make proteins or patterns for proteins, this is how many different proteins you could actually make. 3 times 2, and of course times 1 doesn't change it, but you could make 6 different proteins with these 3 pieces by rearranging them. You got it? And I'm just showing you the math that we know will tell us how many that would be. You take the number of segments and you multiply it, each by the number smaller. There's a word for that in algebra. It's not important. But that would make, you could make, in other words, if this were the gene, and these were the introns and the blue are the exons which we're going to use, I could make 6 different proteins with that one gene. You got it? And remember, the scientists were expecting when they sequenced the human genome to find at least 100,000 genes, maybe way more than that. And how many did they find? They found about 20,000, not 100,000, see. So this is why. Now this is interesting, folks, because if we had some fancy design before, it's really getting fancy now. Would you agree? And just for fun, if there were 8 different usable pieces, the number would be 8 times 7 times 6 and so forth. How many proteins could you make from a gene that had 8 exons? 40,000. Did you hear Dr. Behe last night say that they found a gene in a vertebrate, I think it was, I don't remember whether it was invertebrate or not, but that could make over 40,000 different proteins. You remember that? He mentioned that. Now, it doesn't mean that if this gene had 8 of these segments we call exons that would be used in different orders, it doesn't mean that it will make all of those. But it could, if it was necessary. And just for fun, I looked up a research paper on the BRCA1 gene, which we all have. The issue is, would I have inherited a BRCA1 gene that was what? Mutated, right? That would be my concern. And I didn't take this as far as I should have. That was first discovered in the world of breast cancer, and that's where they got the BRCA name. But we know that it's not just for females. It is, in fact, the risk for uterine cancer is about 10 times higher in a female who has a mutation in the BRCA gene, and many other cancers in both men and women. Prostate cancer, much higher if a man has the mutated BRCA1 gene, and so forth. And this has been pretty well studied in terms of how much more the risk might be. But I just thought I'd show you. I'll have to tell you that when I was reading this research paper, I had to sweat to get my way through it. So I know you don't want to see it. But I want you to notice something. This is exon number 18 in the BRCA1 gene. What does that mean? It's one of the sections. And they are studying this particular section. And they actually know about a common mutation that occurs in people that don't get tumor suppression. And can you tell on the screen which one it might be? But can you see the A's and the T's on the screen from where you're sitting? Can you? At the bottom of the page there? Those are all the half rungs in exon number 18. Y'all with me? You're not nodding your heads. Are y'all lost already? Do I need to do this again? Say yes or no. Do I need to do it again? No. All right. And in position number 1, 2, 3, 4, 5, 6, there is sometimes a T instead of a G. That mutation is found in some people. There are some mutations of the BRCA1 or 2 or some other tumor suppressor genes that don't seem to cause a problem. It's very interesting. But there are some, of course, that are quite serious. So the correct mutation, if you wish, inherited, can be an issue. All right. Now tonight we're going to have the interview with Dr. Carson. And so I want you to understand something about nerve cells, because he is a what kind of surgeon? A neurosurgeon. We get neuro from nerve. And it's true, he's a pediatric neurosurgeon. So in order to understand how a nerve cell works, I want you to imagine a metaphor of a dormitory. In a college dormitory that's unusual, so you have to follow with me how this dormitory works. But let's just imagine that this dormitory maybe is a mile long, stretching from here for a mile, and some young woman wants to get a message sent. And so she's going to give the message to one of the guys in the dormitory who happens to live on this end. And she hopes that the message will get to the other end and get to the right guy or something like that. So here's the way this dormitory works. The men in the dormitory, there's only rooms on one side of the hall. And the men are not allowed to go into their rooms except under one condition. So all down this mile-long hall, every room has a dormitory college man standing in front of his door. Can you picture that? Say yes. And in this unusual dorm, there is a dean for every student. On the other side of the hall, don't say what, I'm making up a story. There's a dean on the other side of the hall whose job it is, watch this, as soon as the guy goes into his room, to pull him right back out. Strange dormitory, but just stay with me. Now, finally, the last rule for this dormitory is the only time a particular guy can go into his room is if the guy next to him got to go into his room. So, the girl comes and knocks on the end of the dormitory, and she has a message. I won't tell you what the message is yet. I want you to figure this out. Because she does that, the first guy gets to jump into his room. What immediately happens? Two things. His neighbor starts to go into his room, and this dean pulls this guy back out. Is that correct? Now his neighbor just went into his room. What happens? Two things. His dean pulls him out, and his neighbor gets to go into his room. And so this effect, if you will, of people going into the room and being pulled back out propagates down the dormitory hallway, correct? And finally, this is where I want you to really put your thinking caps on. When the last fellow enters his room and gets pulled back out, the message has arrived. What's the nature of that message? What does that question even mean? Well, you'll understand this in this day and age, most of you. The message is binary. In other words, there isn't much information there. It's either the guy is in his room for a moment, or he hasn't been in his room for a moment. That's like computers. I don't know if you know this, but when you type, let's just say you type A on your keyboard, inside the computer, I should have figured this out, and I'm not going to waste your time to do it. What's the ASCII for an A? Isn't that a 46 or something like that? Anyway, don't worry about that. Inside the computer, all you have is a number that either has ones or zeros at all the places where there's a number. You pressed an A, but inside the computer, it's ones and zeros. You kind of knew that, didn't you? You've heard that kind of thing. And this thing is racing around inside the computer. And it finally comes back on your screen as an A. I'd love to tell you, but you don't want to know probably. But it finally comes back on the screen as an A. I say finally, in a fraction of a second. Now, the reason this is so remarkable, folks, is this. You have about 100 billion neurons in your brain. It's a lot. And a neuron is almost exactly like this dormitory. Just a little bit of quick physiology. The neuron has we call it the head or the cell itself, and it has this long, in some cases this thing is as long as 2 or 3 feet, even though it's microscopic. These are the biggest cells by far that are found in the body. But there are nerves that travel from the base of the brain clear to the base of the spine before there's a synapse and a new nerve starts. You kind of know about that, don't you? That's a long nerve, see? But the head of that nerve is in some spot, somewhere up there in the base of the brain. And we call this long thing, don't worry about these words, this is an axon, this long thing, where the message travels. That's the axon, if you will, and we're going to take a little bit of an understanding of what happens kind of right there. And down here at the end is where the message finally, that's the other end of the dormitory. And the dean in this case it's little piece of protein, a little protein in the wall, I don't even picture it here, in the wall of the neutron, a little protein that pumps electricity from the inside of the axon to the outside. And it does it by kind of doing this. And it's just amazing. It pumps electricity. Now, for some of you that have a little bit of scientific background, these are actually sodium ions that are electrically charged, positive, and so they get pumped. And that's like the dean pulling the student outside, okay, outside of his room. And when a signal arrives here, what happens is it allows this first piece of electricity to actually travel through a gate, another protein that lets it go in side the cell, like that. Got it? Now, once the last one at the end goes inside, the message has arrived. What's the nature of the message? Somebody remembered. Would the rest of you please remember what's the nature of the message? It's binary. So, this is the amazing thing, folks. This, I think, of all the things that goes on in the body, and they're all amazing beyond description. This, to me, is the most amazing. Because inside your and my head, in our brains, you could call this thing if you wanted to, and you actually can put electrodes on people's and amplify, and you can hear a little click when that last guy goes in. And so a click is binary, isn't it? It either didn't click or it did click. Isn't that binary? Binary means two, like a bicycle. That's where this word comes from, binary. And the only all that's going on in your head is a bunch of little clicks. I know you thought that was your kids' problems, but it's actually your problem too. Now here's the amazing thing, folks. To me, this is mind-boggling. How can a bunch of clicks be made into a thought? Is that pretty amazing? Now, a thought is one thing. What about making a bunch of electronic clicks being an emotion? Is that a ponderous thing, an emotion? Isn't that amazing? And of course, what's happening? There might be 50,000 of these things hooked around here. In other words, places where a message could come in. So this is a way oversimplification, but it's like maybe I could get a message to go through this pathway, and you will hear Ben Carson speak about the fact. I ask him this question. I say, will we ever figure out how a thought is created? Well, in fact, the place where he says there's a pathway is, I say to him, do we know how memory, how is memory stored? And he says, no, but we do know this. There are biochemical pathways laid down. What is that? What he means is that, and we have ways now of examining the brain while people are thinking, and we have them watch something or think about this or that, and we can see places light up in their brain where there's more chemistry going on. And this is why we know what takes place in the brain everywhere down to about a millimeter. We now have the thing mapped. When a certain thing is going on in your mind, we know where it's taking place. We know, and we'll look at this Thursday evening, we know where the center is where the optic nerves come and vision is created. And by the way, this is the same thing. The only thing that's coming from your eyes, from the retina, is a bunch of electronic clicks. And it turns into what when you've got your eyes open? A picture out there. It's astonishing. So there are these pathways. What does that mean? Well, I'm sure you all know this. One of the amazing things about the nerves in the brain is none of them are touching each other. There's little spaces. Now, in this room, for that light to come on up there, there's a wire somewhere that's touching another wire. Is that right? And the switch, when you flip it, untouches, so there's no more light. But in the brain, everything is untouched. And the way this happens, and most of you know this, we call this the synaptic cleft. You've heard of that, haven't you, before? Synapses, right? And when the last little piece of electricity jumps in, it causes these vesicles, which the cell makes. The cell manufactures these little balloons and fills them with neurotransmitter. You know that word, don't you? Neurotransmitter. It's chemicals that when the little, did you see that? When this little thing jumps over to the edge, and when it touches the edge of the nerve cell, it's like kind of a soap bubble that touches another soap bubble, and suddenly they're one. You know that idea? And when that little thing touches the edge of the cell wall, it's like the cell wall opens up. And by the way, just a few months ago, 2 guys were given the Nobel Prize for figuring out how that thing opens up when it touches. But you get what I mean when I say it opens up? And the contents of that vesicle, this chemical neurotransmitter, spills out across that synaptic cleft, and there are receptors over here on this nerve cells, just like, how many of you have ever heard the term receptor? It's on all of our cells have these little things sticking out, like the ladies sticking their hands through the holes. And the receptors are waiting for the right shape to come along. The receptors are proteins, which are made by the cells, by factories that were made of protein. You got all of that last night, didn't you? And when the receptors on the receiving nerve cell are activated by feeling this chemical, then the signal carries on. You got it? Signal will travel, I don't have it pictured, but the signal will travel on down this nerve cell. And I've drawn some dots there to indicate the receptors on this cell that are feeling this chemical that comes out there. And the idea is that if I keep using a certain pathway, I get to the point where, well, I need to back up and tell you, when you first send that signal to the next cell, it does nothing. You got to tell it about 10 times, and then it sends the signal on. And some kids it takes 20 times. We know about that. Yeah, Joe says, why am I looking at him? I did that joke because I know you know that. That's what it was about. But the idea is that if you get enough neurotransmitter, because the more you use this, the more it tends to get out there, I can get this cell to fire immediately without coaxing it 10 times. You all with me on the idea? And so you establish these pathways. We have no clue, friends, yet how memory takes place. It is amazing what we do not know. We have no clue, none whatsoever, how in the world a bunch of electronic clicks make a thought. Now that's a thought worth thinking about, isn't it? I never cease to be amazed. I think you would say the same thing. And it's this kind of thing, folks, that scientists come along and they say, this thing was designed. Does that make sense? This thing was designed. The complexity is as as Michael Behe said last night, outrageous complexity. And Antony Flew said, inordinately integrated complexities. Stuff doesn't just work alone, does it? Everything affects everything, remarkably enough. Well, so with use, we get more neurotransmitter, and somehow this is how we remember. Now, another very interesting thing is this. We know of over 50 different kinds of neurotransmitters. You all heard it. You all know of norepinephrine, but there's many, many more than that. And one of them, called GABA, it's the letters of a long chemical. We have learned is an inhibitory synapse. What would that be? If you can pour out some of that stuff there, it will stop this signal from passing on. An inhibitory synapse. Y'all with me? And they're everywhere in our brain. It's like as though there is some way to control your thoughts. Now that's a thought, isn't it? And I didn't know this until recently. I was reading some literature on Ambien. Ambien, I don't know if the name of this neurotransmitter is GABA, G-A-B-A. Anybody ever heard of it? Let me see your hands. Yeah, a bunch of you know that. Ambien is a GABA inhibitor. You take Ambien, the things that would normally inhibit you from getting sleepy quit, and you get sleepy. I guess that's the way it works. You got it? Interestingly enough. Well, let me give you one more little nugget here. You all know about brain waves. And when somebody is flatlined, we say they're dead, clinically dead. Even though if we keep them breathing, depending on the injury, their body could live for a long time, even though their brain is not functioning. You all know about that. Here's what's going on. There is this constant firing of cells that goes on all the time, even when you're not thinking. Actually, I don't know if you know this, you can't not think. You ever tried to think about that? But even when you're just relaxing and not thinking, excuse me, kids do that. They know how to do that. I'm just being, I love kids, and you do too. But even when you're not trying to think, there's this, this is what makes consciousness. We can't even define consciousness. I don't know if you know that. We can't even define it. We know what we mean by that. The person is awake. They can hear, they can talk, they can think on purpose. When you dream, you're not thinking on purpose. That's an interesting world too. But in any case, this huge 100 billion cells, and remember, each one of them on the average is connected to 50,000 others. So there's this network, this unbelievable network in there. And there's just firing going on all the time, and that's normal. But the firing ebbs and flows. And when we're awake, it's ebbing and flowing at about 10 to 15 times a second. The ebbing and the flowing, the increase and the decrease in all this signaling. We don't even really understand that, but we can measure that because all these clicks can be detected with electrical probes, right? You amplify that, and you put a probe here and a probe here. There's a voltage difference there. You can amplify it, and you can hear the clicks if you turn on a speaker, for example. So that's what brainwaves are, and that's a whole world of study, of course, itself. Well, I want you to listen for some of these things while we talk to Ben Carson. And here's what I like to do when we're done with that. If you have questions about what he was talking about, I may not be able to answer all of them, but he and I have discussed the things that we're talking about here for hours, and so maybe I could shed a little light if questions come to your mind on the things that he says.
very pleased to have Dr. Ben Carson with us today. Many of you will know the name. He is probably one of the most famous neurosurgeons in the world, the author of 4 books, and the 5th one just about to come off the press, America the Beautiful. I hope you get it and read it. I've just talked with him about it, and it sounds very, very, not only meaningful, but very practical for today and what's happening in this world. Thank you, Dr. Carson, for taking the time to be with us with your incredible schedule.
My pleasure.
And a baby shower for your oldest son's wife this evening.
Actually, my middle son.
Middle son.
Right.
But let's get right to the issue here. The things what we're talking about is God's hand, and as opposed to what the evolutionary scientists think were accidents,
yes,
by random mutations. Talk to us about the structure of the brain. That we've talked about the complexity inside a cell, but just the structure of the brain that creates this thing we call the mind.
Yes.
How has it come to you about how this could ever have been by chance or really was the hand of a creator?
Well, you know, as a neuroscientist studying the brain, it's very difficult to understand how anybody could think something so complex could be so random. I was once listening to Ed Taylor talk, the man who's credited with the invention of the atomic bomb, and he said, well, it was just a bunch of promiscuous biochemicals. They got together, and it all happened. That requires a lot of faith. But in fact, you know, when you look at the human brain, you're talking about something with billions and billions of neurons and hundreds of billions of interconnections. And it can process more than 2 million bits of information in 1 second. It remembers everything you've ever seen, everything you've ever heard. And just for some of the most simplistic things that we do, there's so many pathways involved. You know, just to divert your eye from a dark area to a light area, all the things that have to happen for you to do that, you do it in a split second.
Yes.
But, you know, you've got all these impulses coming through your brainstem, coordinating the various nuclei, the medial longitudinal fasciculus, they all go through there, back up into the back part of the brainstem. You know, you have another set of parasympathetic fibers that have to be involved to cause the pupils to constrict when you go from a dark area to a light area. And then you've got the muscular move. I mean, it's unbelievable, all the things that happen for just the most simplistic thing, not to mention anything that's complex. And to imagine all of those things somehow just randomly occurring really stretches the limits of credulity, quite frankly. And, you know, a friend of mine, Francis Collins, who is the director of the National Institutes of Health, was an atheist when he started his graduate studies. And as he began to unfold, you know, the mysteries of the human genome,
yes,
he said, this is way too complex. This is way too sophisticated. There's no possibility that this could be random. And he became a believer. And that is really quite an amazing story. The #1 scientist in our nation became a believer after an objective look at science.
So have you had much opportunity through the years to dialogue with people who were not believers, shall we say, or scientists who seemed to be objective, perhaps, to you, and yet couldn't leave the evolutionary paradigm?
Yes, I've had many such conversations, and you know, unfortunately, a lot of, quote, scientists are not objective because they start with the premise that the whole concept of God is silly, and that's for non-sophisticated people. So everything is then filtered through that kind of belief. You know, it's just like with Christians, we say, the love of Christ constraineth us.
Mm-hmm.
Well, everything that we do and believe is filtered through that belief. So they are exactly the opposite. So that's the kind of thing I think that makes it a little easier for them to accept some pretty
Illogical.
ridiculous things. You know, I mean, for instance, where did matter come from? If there is no God, there is no creator, where did it come from in the first place? And okay, so we got some matter. And then where did this big explosion come from?
Yes.
This big bang that completely organized everything.
Mm.
Because the fact of the matter is, if you believe in the second law of thermodynamics, which is entropy, it says things tend to move toward a state of disorganization,
Yes.
not toward a state of organization.
Yes.
So here you are injecting enormous energy into a completely disorganized system, and instead of it becoming more disorganized, it becomes completely organized.
Yes.
To the point that, you know, we can predict 70 years hence when a comet is coming. It's that organized. In a way that the Earth rotates in a very, very periodic way, so that you can predict the timing. The way that the various planets in our solar system are structured to shield us from what would be death rays from other parts of the universe, that we could be precisely the right distance from our own sun, which is really quite a small star in the whole complexity of the universe. You know, that is really quite a lot to happen
By accident.
by accident.
By random.
And that requires an enormous amount of faith. But then, let's say you say, okay, we'll give you that. We'll give you that. All that happened, it was just an accident, but it was perfect, and the right environment existed on the earth. Now you've got to create life out of that.
Yes.
So when you look again at our brain, you look at these frontal lobes of ours, which have the ability to extract information from the past and from the present, and to assess that and integrate that and project it into a plan for the future. I mean, how does that come out of a slime pit of promiscuous biochemicals? That is really pretty amazing when you think about it. And then you think about a thought. And, you know, where does a thought come from?
Well, I wanted to push you into that area a little bit, because tell me if I understand this correctly. The signals that take place in the neurons are really binary. They're either zeros or ones, if you wish.
Mm-hmm.
And so what's going on in our brains is a bunch of electronic clicks.
That's correct.
How can clicks become thoughts or emotions? Talk to us about that.
Well, you do think about it. I mean, what happens initially to start any kind of impulse? You know, you have these membranes, these cell membranes on the neurons, and in order for an electrical impulse to occur, first there has to be a chemical reaction. You have a sodium-potassium pump, and as they go across that lipid membrane, it then creates another reaction, which begins to create an electrical impulse, which continues to propagate, polarizing and depolarizing the membrane all the way down an axon. Each one of those axons or cells is in contact with at least 50,000 others, and you know, this is going instantaneously to all of these places, and it's coordinated, and then it gets to a part of your brain that we call the hippocampus, where there is an interaction with things that have happened before, with memories, all of this occurring instantaneously. Then you have to retrieve a memory through something we call the tract of Victor Jour, which travels back around to the mammary bodies, And then that has to come back and interact with your frontal lobes, with your reasoning process. Instantly, all this is happening because we're having a conversation. You can ask me a question, I can respond instantly, and yet all of those things had to happen in order to be able to do that. I mean, that is really almost incomprehensible.
Complex beyond imagination.
Complex beyond imagination. And with all of the sophisticated equipment that we have, the electrophysiological equipment, the EEGs, the MRIs, the PET scanners, positron emission tomography, which allows us to see the metabolic activity that is occurring in the brain cells instantaneously, the functional MRIs, all of these things that we can study, the physiological processes that are occurring in the brain, and yet we still don't know how a thought is generated.
Yes.
We still don't understand what the mind is. And I don't think we ever will, because these are not tangible things. These are the ways, for instance, that we are able to communicate with God. And, you know, why we are different than all the other creatures, because God said, let us make man in our own image. And part of that was this incredibly sophisticated, you know, cerebral apparatus that, look at the things that have come from it. Computers.
Yes.
You know, the space shuttle. You know, atomic bomb. You know, how did we get so smart that we could figure out at a subatomic level that you could energize an atom, and that you could utilize that in a way when you pull it apart
to get some energy.
I mean,
a lot of energy.
I mean, think about that.
Yes.
I mean, this is pretty amazing stuff.
Yeah, I visited a factory one time where they were making computer chips, and it just blows your mind that people's minds were able to design all that stuff and then make the machines that make it happen.
Right.
It's just incredible.
And you know, I think about that very frequently when people say to me, I can't do this, or I'm not good at that. I frequently run across young people who say, you know, I'm pretty good with philosophy or history, but I can't do math.
Yeah, I've heard that.
Calculus, I can't do that stuff.
I can't do science.
Right, which of course is totally fallacious, because anybody can do it.
The capacity is there.
It's there. It's just a matter of, did you program the computer correctly? Computers are a piece of junk unless it's programmed. Yes. And it's the same thing with our mind. We program it. But it's very important that we understand this with our young people. Everything that your mind takes in becomes part of its programming, and it stays there, and it impacts who you are. It impacts how you react to things.
It affects how you think.
Absolutely. So if you think it's perfectly benign to take in something, yeah, it's okay, you know, believe me, it is affecting who you become and who you are.
Now, we really yet do not even know how memory occurs. Is that correct?
Well, we do have, we do know some things. For instance, we know that there are biochemical pathways that are actually laid down, fortunately bilaterally, in the hippocampal regions of our temporal lobes. And we also know that if, let's say we take a certain type of electrical probe and we could place it into the hippocampus of an 86-year-old man, stimulate.
And a mild voltage.
Yeah. And he could quote back to us verbatim a book in its entirety that he read 80 years ago.
Even though he doesn't have a photographic memory,
exactly,
as we say.
Because it's all there. It's all there. And it's a matter of learning to recall. You know, a lot of smart people teach themselves how to recall. There are lots of tricks, mnemonics, and various kinds of things for teaching yourself to recall. And it's a matter of practice. I remember when I was in medical school, and, you know, we had to learn enormous amounts of material. They say the first 2 years of medical school would be akin, in terms of the amount of material you have to learn, to learning 8 new foreign languages simultaneously. And one of the things that I started doing was memorizing, you know, passages from the Bible, whole chapters from the Bible, and it gave me a facility with memory that translated into everything that I was doing. So, you know, it's just like any other part of the body. You know, if you want your biceps to be strong, you got to use them a lot. You can't watch somebody else use them and then yours become strong. You know, it's the same thing with the mind. You know, you have to use it. And it's one of the reasons that I think there's a lack of creativity in our societies. You know, our social and developmental psychologists tell us that 98% of babies are creative. And really, all you have to do is sit there and look at a baby. I mean, they will take just the littlest thing and they will just have a ball with it. You know, they'll have more fun with the box than with the toy that came in the box. But that's because, you know, they're very creative. Those same psychologists tell us that by the time the average young person in our country is age 16, only 3% are creative. So what happened to all that creativity in the meantime? Well, same thing that happens to your muscle if you don't use it. People sit around and they watch television and movies and they play video games. And they do all these things that required a fair amount of intellectual investment by someone else.
Not by them.
But not by them. And consequently, they become less and less creative, less and less imaginative in the way that they do
Now,
things.
this matter of remembering everything, would I be correct in saying that there is some physical change in the brain, a pathway, if you will, that takes place to record the memory?
Yes.
And when God created Adam and Eve, for those who believe that, did he not intend for them to remember everything they ever saw or heard for eternity?
Obviously he did.
So in a finite space, you can record
Everything.
Isn't this mind-boggling beyond belief?
It really is. I tell young people all the time, because I hear people say, don't read that, don't study that, don't memorize that, because there's only so much space, and you'll overload your brain. And I just have to laugh anytime I hear that. I say, you know, within your brain, there is plenty of capacity to take in everything that has ever been written by anybody in the history of the world, and you won't even begin to have taken up all the space. So you really never have to worry about overloading your brain.
A terabyte is nothing in comparison to the brain.
Well, the brain invented the terabyte.
Years ago, you became well known in the world because you separated the first occipital joined twins. Actually, before that question, I wanted to ask you this, and if we get time, I want to go to that. You also became well known for doing what's called a hemispherectomy.
Right.
And tell us about that. Isn't this because some child becomes an epileptic or something?
Yeah, they develop intractable seizures, which means there's no way to get them under control. And there are certain disease processes that seem to occur in one half of the brain. Rasmussen's encephalitis, some congenital vascular anomalies, some neuronal migrational disorders where the neurons just don't develop in the right way on one side of the brain. And the seizures are devastating. And
can't control them with medication.
Can't control them with medications. The first hemispherectomy I did, the little girl was having 130 seizures per day. They had tried everything to get it under control, including putting her in a pentobarbital coma for 2 weeks in Denver. And
she wasn't having seizures while she was in a coma.
No, but the minute they woke her up, they started up again. And the reason that that I got involved in them is because one of the pediatric neurologists, who's quite senior, had seen a time when people had done some hemispherectomies, but the complication rates were just
enormous,
beyond belief, so they kind of fallen out of favor. And he said, would you be willing to consider hysterectomy in this girl? So, I went back, I read all the literature.
For the sake of our listeners, we're talking about removing half the brain.
Correct.
Correct.
That's correct.
Which sounds like you're dead.
It does sound pretty awful. But I started trying to figure out why there were so many complications. And one of the reasons was because people really didn't have a good way of imaging what was going on. So there would be bleeding, there would be hydrocephalus or accumulation of fluid, various types of things, and they would be just trying to guess what was happening. And of course, at the time that this came to my attention, it was 1985. We had CAT scanners. We had just gotten MRIs. So, and also there was this chronic bleeding that would occur. Well, we had some agents that would help take care of that now that they didn't have 20 years before that. So I said, I think we can do this. And, it was pretty amazing. The first time I did a hemispherectomy, when the little girl came out of the operating room, there were cameras and there were all kind of things. And she said, Mommy, Daddy, I love you. Everybody was like totally blown away. How in the world could this happen? Well, why is it possible? Because if I were to do a hemispherectomy on you, it wouldn't work. Yeah, and you would just like be gorked out. Well, there's a phenomenon known as plasticity. The neurons in an immature brain have not all decided what they want to do when they grow up yet. So you can actually recruit neurons on the other hemisphere to take over some of the functions from the lost hemisphere. And that's why it can work. And, since that time when I started doing them in the mid-'80s, there's been lots of advancements on hemispherectomies. A lot of people thought it was really weird. I remember getting a phone call from a bunch of medical students in Boston at a very prestigious medical school. And they said, is it true that you can do this operation? Because we talked to the neurosurgeons and they said we had misunderstood what we heard. But in fact, that's what advancement is all about.
How do you recruit the neurons to the other side?
Well, you don't physically recruit them, but it's just that they're very, what we call plastic. So a neuron that is sitting in the right frontal parietal region, instead of just, doing a motor function that controls the opposite side of the body, can now, the body says, you know what? We've lost all of the neurons on the left hemisphere. We need you now to do what those neurons would be doing, and it can actually learn how to do that.
This is just astonishing that God built into the brain the capacity to, what shall I say, fix itself,
yeah,
in a sense.
And this phenomena of plasticity, which really we began to study because of what was happening with hemispherectomies, is going to help us out tremendously, because now we're starting to learn how to take mature cells and to de-differentiate them back to a more immature level. This is one of the reasons that we're making so much progress with stem cells now. Instead of just using embryonic stem cells, we can take mature cells, move them back, and then redirect them. And in fact, those seem to have less proclivity for turning into cancers and things. So this is tremendous. But when we learn how to do that with some of the neurons in mature people, and then people who've had strokes and other types of phenomenon, we might be able to do this. And then when we can add stem cells to that and recruit them to do the right kinds of things, it will be pretty amazing what can be done. All of this, though, goes back to what we were first talking about, the incredible sophistication of the human mind, of the brain. Things that can be imagined, almost anything that we can imagine, we can figure out a way to do it. And that's because we're made in the image of God.
Oh, it's just astonishing, isn't it? Well, we have a few minutes left. Talk to us a little bit about why the occipital
Craniopicus, yeah.
was so difficult to work on.
Okay, well, conjoined twins, which, formerly were called Siamese twins. And the reason they were called Siamese twins is because the most famous set, Chang and Ing, were born in Siam in the year 1811. And they made Barnum and Bailey famous, travel all over the world, ended up here in the United States. Never got separated, but the term Siamese twins stuck. But occipital craniopicus are twins that are joined at the back of the head. And the blood flow in the brain, as it's drained, all drains to the back of the head, an area that we call the torcula. And it drains very, very rapidly, so that if I were to put a hole in your torcula, like the size of a pencil, you would die very, very quickly. You would just bleed out. The blood pressure would get very, very low. Air would suck in there. Air would go to your heart. You would be dead in no time. And that's what has happened traditionally when people have tried to operate in that area, because you've got this confluence of sinuses coming together, plus you have the abnormality of another one coming in and joining it.
So two together.
Right. So trying to deal with that, even with extraordinarily skillful people, incredibly bright people, it just never turned out. And in this particular case with the Bender twins, I'd never done any conjoined twins, but I got really, really interested in conjoined twins and started reading about them, trying to figure out why the results were so dismal, and I discovered that they just all bled to death. And I was talking to my friend Bruce Wright, who's the chief of cardiothoracic surgery, and he'd done a lot of work with hypothermic arrest, where you cool the body temperature until the heart stops, pump all the blood out, and then you can operate on an infant heart for up to an hour. And I said, if you use that at just a critical time when you were coming to that part of the separation, and you could get through and then reconstruct those vessels, and then pump the blood back in and then start the heart back. And then I said, why are you thinking about such a silly thing? First of all, you're never going to see a set of twins, so forget about it. 2 months later, here they came. And, I explained that, and everybody said, that sounds like it could possibly work. One of the real advantages at being at a place like Hopkins is you have really top-notch people from every specialty, and we started putting the plan together and figuring out exactly what had to be done, and it worked.
If I remember correctly, you said that to rebuild that vasculature, you needed to use, at least you chose to use pericardium.
Cardiac.
So you had a thoracic surgeon in the chest,
right,
giving you pieces of...
And what was really amazing about that is that the cardiothoracic surgeons were actually looking at what we were doing, because
give you the right size.
They had to give us the right size and the right shape, because we only had an hour of hypothermic arrest time. Everything had to work like clockwork, and we finished at 59 minutes and some seconds. We were able to turn things back on. And that tells me that as skillful as we were, I believe we had some additional help.
God's blessing.
Absolutely.
Well, thank you, Dr. Carson, for taking the time. I think this will delight our listeners and help them solidify their understanding that we were created beings with astonishing capacity, far beyond what we can, even with these minds God gave us, imagine. So thanks for it.
Well, thank you.
Sorry that we don't have a stereo output of the computer, so the music was on one channel and my voice on the other. You couldn't hear what I was saying, but it doesn't matter what I was saying, so that's all right. Let's take a few minutes if you have questions about some of the things he was talking about. Maybe I can shed a little more light on them. Yes?
So when you took those twins apart, did he have to reconstruct like a hard skull there?
No, not necessarily. The thing he was talking about is the torcula, which is this chamber where everything drains. They cut that in half. So,
Is there a hole in the skull and the child?
oh, sure, but they use plastic or something. That's not an issue. It's just, they have to protect that. But they have to rebuild that whole vasculature for each of the two. And what Ben actually told everybody was, there was about 52 people in the operating room. This thing was well rehearsed and all planned out. And he told everybody, I don't want anybody to say a word about time. And he just worked as quickly as he could. And when he got finished and made the last suture, it was about 15 seconds before 1 hour. It was just very, very interesting. Yeah.
I just want to know the purposes of those two.
They lived. I haven't heard that they have passed away, but they lived. There were compromises in their capacity, but they did quite well, actually. They were from Iraq, if I remember correctly. Somebody else remember that? Yeah, twins. Anything else in the whole scheme of the things he was talking about?
I don't know if I can explain my question, but child who had the part of her brain.
The intractable seizures, and they did a hemispherectomy. Did you all understand what he was saying? They remove half the brain.
So if I think the right side is creative and the left side is analytical, was she able to mature both sides of her brain in that one brain, or was she just creative?
Yeah, it's very interesting because actually this left brain, right brain thing, you may not know this. This has been debunked recently in the literature. Have you all heard that? Anybody heard that? Yeah. We've all heard that for, 25 years, but it has turned out to not be true, interestingly enough. Well, the interesting thing is this, that, and I asked him this question in a way that he ended up not answering it. I asked it poorly. The question I wanted to say was, how do we recruit the neurons over there to do what used to be done over here? And it sounded like I was saying that they were physically moved over. But anyway, the answer, he and I have talked about all these questions, walked around for hours discussing all this. This is why I have this background, is the only reason. And I don't know if you caught this. He said that memory was laid down bilaterally. Did you catch that? That happens all the time. Now, we don't know how memory occurs, but we know where it occurs. It's in the hippocampus, which is kind of right in the middle of your brain. If you went straight in from the temporal lobes, right about there, that's the bottom of the brain, right about there. And it's this region, a semicircular region, and whatever we learn is stored in both sides. That happens all the time. And what the physicians and scientists learned was when a child is having problems with the way the brain is working, the brain by itself starts copying stuff that's on the other side. So that, and they can tell, they can examine the child neurologically to see if that has happened yet, based on the fact that they've gotten these seizures and are sick. Y'all with me what I'm trying to describe? And once they can tell that has happened, they can take out that half and the child is perfectly normal. But he's talking about, this is what he said, when the brain is still immature, in other words, it's still developing, and we didn't even know some of this until recently, the child's brain continues to develop and grow I don't mean necessarily physically, but in terms of connections, and some neurons are growing, appearing as well for quite some time. This doesn't happen for adults. There's a time, probably in about the mid-teens, where it's finally finished, and after that, hemispherectomy could be done, perhaps, but there would be no plasticity that had developed to take care of the problem that was occurring on the other side.
Did they have to fill the void?
When I asked him that question, he laughed. He says, everybody asks that question. It turns out that the cerebral spinal fluid, before you can hardly finish the job, fills up. And so, and by the way, and so that takes care of it.
So the other half of the brain doesn't expand?
No.
Use some of that space?
It's, in spite of the fact that brain is pretty much like tapioca pudding. And you know, physicians are awful. What they joke about is awful. So they have this little scoop. This is the funny story. And they're scooping away some problem with the brain. Oops. You know, you don't want the neurosurgeon to say oops, do you? Oops. there went algebra 1, you know. But I mean, it is so soft. It's not like you're having to cut a piece of apple out or something. It's just soft.
And the other side doesn't fall over into
No, amazingly enough. Over here, and then we'll come back. You were first. Go ahead.
How do they backtrack the mature cells?
I don't know the exact details on that, but I can give you the general answer, and that is that the way we take a stem cell in the laboratory and make it become any kind of cell we want, we can do that. A nerve cell, a beta cell in a pancreas, a muscle cell. It depends on what you feed it. The chemical soup that you feed it, we have learned by just trial and error. And so it is something like that to make the cell, if you will, backtrack. The way you nurture it, and then when you get to the place where it is now a stem cell, you feed it differently, and then it makes something you want it to make. It's very, very, but it was a fascinating point, wasn't it? We don't need to use embryonic stem cells, and I don't know if you picked this up. This is a very interesting issue. One of the big problems with stem cell research has been you plant a stem cell into the brain, and it not only makes a nerve cell, it makes a tumor. Just keeps growing. It's a very big problem. And it's not cancer. He called it cancer. It's cancer in the sense that the thing is growing uncontrollably, but the cell hasn't become cancerous. It's just a stem cell that, because it isn't in the milieu of what it was when it was supposed to be making a fetus, it doesn't have signals to tell it to stop growing. And what he said was, when you take a normal cell and bring it back and then reprogram it, you don't have this problem of making a tumor is very, very much lessened. Did you catch that now that you hear me talk about it?
Very interesting thing from his teaching when he said how wonderful and powerful our brain is. And then he said something afterwards. Now we know why we are made in the image of God. All I can praise God through what he was saying.
Yeah.
Absolutely fantastic.
I picture myself someday in heaven going to class. Have any of you thought about that? Oh, yeah. I'm going to sit on the front row, Tom. I think. Now, maybe they'll line us up according to smarts and I'll be in the back row, but I'm going to... And I just got all kinds of questions. I mean, won't it be fun? And not only that, the instructor's up there, and maybe the instructor is going to be Christ most of the time, because actually he's the one that made this stuff. Is that correct, according to the Bible? He can take you into the laboratory and show you. Wouldn't that be cool? And the electron microscopes up there are going to be much better than they are here. Are you all with me on this? There's nothing you can't see that you want to see. Wow. I can't wait. Wouldn't you all like to go to school again and learn something? That's the way I feel all day long.
Could you talk maybe or explain a little bit about deep brain stimulation in people who have MS?
No,
How that's where you can...
I don't have much knowledge about that. I know a little bit, but not worth talking about. Somebody ask me a question I know.
The scenario of the 80-some-odd-year-old man with the probe, was that hypothetical or was that...
Oh, no. This has been known for 40 years.
So can they now do that with people who have memory loss or problems with memory?
I don't know that people have tried to do that. That's an interesting question. Here's how about using this in solving crimes? But what was done years ago, this was actually done in Montreal. They would remove a piece of skull under local anesthesia. Person is awake. And they insert a probe. And it's quite a ways from here down to the hippocampus. But it's a microscopic probe, so it does very little damage as it's going in there. And they get down into the hippocampus, and you couldn't hear me say this because of this mix-up with the stereo thing. They apply a mild voltage, and suddenly this person it's in real time. They're sitting there and listening to the orchestra. They can tell you everything that people are wearing. They watch them draw the bows back and forth. The whole thing is stored. And you heard me say to him, you didn't hear me say, even though they don't have a what do we call it, memory, a photographic memory, we all have photographic memories. It is all there. And the thing that blows me away is there is some physical change in there to store the information. Did that make sense to you? There has to be. We don't know what it is. We don't understand how it is. But that has to take up some space, right? There's something been done there. That's got to stay there. And how you could do that for eternity, everything you ever heard or saw is the mind-boggling thing. And his answer was, it's because we're made in the image of God.
So when the probe was taken out, did he still have that oxygen?
Oh, no. It's only when that area is being stimulated. Now, it seems to me that one of the most profound things in this discussion was his comments about programming the brain. I don't know if that came home to you real strong. And we've all done some poor programming, haven't we? His thesis, or his theory is that everything you watch or listen to, or maybe even think about, is programming your brain. That is profound stuff. And it scares me for our kids. It scares me for our country. You look at please don't misunderstand me. My life is wrapped up in kids. I taught kids for years, and of course I have children. But I am in despair about how little they think. It's crazy what we let kids get away with in terms of not thinking and not being productive. And the problem is, it's not just what they're doing now. That's what it implies for their lifetime because of the programming. That's the point I'm making. Does that make sense to you, what I'm trying to describe?
Yes.
Yeah.
How does a smell or a taste revive an old latent memory?
Well, we don't know precisely, but it's not too hard to conceive of the fact that there's this memory pathway laid down, whatever that is, right, that's connected with an odor. And so that stimulates that memory, kind of like the probe did with a little electricity. You know this, folks, if you understood this thing of the electric charges moving, the whole brain operates electrically. Even the neurotransmitters, they fit, but it's also an electrical fit. Did I tell you that the pluses and minuses have to it's all electrical. It's just astonishing. And it's such a tiny piece of stuff up here. I don't know. Let me take a minute to tell you a story, but okay, we'll do this first. I mentioned it in the conversation, and I was doing a series of lectures. Actually, they were Bible lectures in Salt Lake. And a young man came up to me, I don't know, the first or second night, and he said, I work at Fairchild Semiconductor. And I used to teach electronics, and I taught the students how chips are made, how computer chips are made. Now, I'd never seen it. I just read it. But I'd love to see it, right? And I said, so where do you work? He said, I work in production. You know what that means? He's making them, right? And I said, wow, would you see if your boss would let an old physics teacher come in there for a tour? And so he did, and I went there, and they dress you from head to toe because even a speck of dust will make the chip quit working. And it's astonishing, folks. Upstairs, there were two levels in a room 3 times this big. They had tables maybe as long as from here to the wall, about as far as you could reach halfway across. Pretty wide, 6-foot table. And there were engineers up there drawing lines on pieces of paper that were laying on these tables. These lines are going to become wires. And they're drawing lines, and they actually know how to make one part of a transistor by drawing a line a certain way. And because there's going to be another layer under that has the second line, and another layer under that that has the third line. So all three of those lines in the end are going to become a transistor, that kind of stuff. And these guys and ladies are up there drawing these lines on this paper. And maybe there's going to be about 15 pieces of paper that they take a picture of, as big as I was describing, and make it down to something about 1/8 of an inch on a side, a little longer. And you go into the production fabrication room, and they have grown, they have made some silicone, like our silicone rock, and they slice it off into thin slices. Just looks like about a CD without a hole in it. And it does have a tiny hole because they put it on a thing that makes it spin. And then this machine comes along and exposes 10,000 of those pictures on that CD size thing. And then a robot comes over and squirts some developer on it. And if you get a microscope, you can see those lines that were drawn for that one level. Then they put another robot comes over and squirts on some stuff, and you have to make holes. If you can imagine this, if you want a wire that's going along here to connect to a wire that's going along here on a different layer, there's got to be a hole between the layers so the wires can touch. Does that make sense? And I'm telling you this whole story, folks, because men and women dream this stuff up in their brains and draw these lines. And this goes on till there's about 15 layers with insulation between them. And all the transistors are made by having 3 layers connect just right. They have to draw the line just right to make the 3 parts of the transistor and connect wires to them that they draw. And they make capacitors and inductors by drawing lines. And this electronic circuitry, that's the chip, is created. I stood there and watched the whole thing. And then I said to him, I'll come back to him in just a second. Could I have one of those things? And he said, yeah. Every once in a while, when the robot comes over, something goes wrong and they have to throw that whole thing away and start over. And they gave me one. And I used to carry it around when I do lectures, and one day it broke. Feel real bad. Anyway, go ahead, Tom.
I just wanted to comment that probably happened by an explosion in a junkyard.
Yeah, I know. I don't want to make fun of the evolutionists. But, and I mean that, friends, don't do that. The evolutionists come to this posture by saying there cannot be a God. There cannot be the supernatural. So I'm going to have to figure this thing out, how it would have happened some other way. And of course the problem is the odds are just way, way, way out of line. And so what they finally say is, well, it's here, so it had to have happened. And so we all need to keep thinking. And of course, I think you get the point, folks. I have respect for these people, but what I want people who are willing to be believers is to understand that we have a divine designer and creator that is unspeakable, as the Bible says, and full of glory. Now that's an interesting term. But anyway, Lance, you had... Oh, okay, Carmen, yeah.
So that piece of silicone that they do that to, is that just one chip or they cut that into many?
10,000 chips on that one piece. And once they do all the layering, they have a machine that comes along and tests every chip. Now they had to build that. Think about that. Has a lot of little wires that go down in there the right places. And they actually had in the hallway as you came in a beautiful display with a light shining on it, they have one of these where every one of those 10,000 chips worked. So they saved it, because usually there are some that don't. Some little minor flaw in this whole process. And they actually, then they have a little saw that cuts those things up into that shape. And they put them in a box with wires that connect to all the places that have to be connected to. And the box has to be big enough to fit on a board where other wires can hook to it. You've all seen that, the chip that goes on the board. The chip that the Pentium 5 chip or whatever it is that you put in your computer, those of you that ever built a computer, is way, way bigger than the actual chip in there. But that's just a physical thing that's a heat sink partly, and it's got all the wires that have to, it's just phenomenal what men and women do with their brains. Yeah.
By the time the child is like 16, they've developed who they're going to be, basically. I think that's kind of what he's saying.
Yes.
But all the things they're taking in, all those impressions, our government is saying, oh no, these young people are out killing people, and these young people are, doing all these
It's not coming from their video games. All those people they're shooting on their video games, that's not why they go shoot their teachers. No, no, no connection.
It's so ridiculous.
Yeah, it is to me.
Anyone can't see that.
Yeah,
And any parent that allows the children to do
Yeah.
that, it's very sad.
yeah,
Because they are trying, what they're doing is creating that next kid that goes in the theater or something.
yeah. Although, interestingly enough, the social scientists have done the research and claim that they cannot show a connection. I think the research is faulty, I really do, but I'm sorry.
Just, I've built circuit boards before.
Sure.
That you were explaining, that's just a bigger.
A bigger model of the little bitty one.
That's the old M84.
Yeah, yeah.
And I've installed fiber optics. I don't know how it works. I know that the diameter of your hair is 188,000 phone lines that go through there. How does it know it's me over there when I answer the phone?
I know.
It's a light.
Her comment/question actually sparked a question.
Speak up a little bit so people can hear you, yeah.
Her question sparked a thought I want to run by you, or a question. I know that in some examples, when people are saved, they go from a life of like, that's sometimes very extreme, and change overnight, or change over in a moment. So I'm wondering what's happening in the brain to make those changes. Like, those pathways are completely reverted in a second? Or
This is a very...
they're harder to
Say your first name again.
Andrew.
Andrew. This is a really interesting and deeply probing question. Because, and if you want to get some very interesting reading, how many of you ever heard the name Josh McDowell? Good. Read some of his books. The stories of people who, like himself, if I can say this, were profligates. And when they decided to be a follower of Christ, became nice people. You all with me on this? And I think it's a miracle, but I do think that this is my opinion. You can throw this out anytime. I think that when we give God permission, He can influence the way the electric currents flow in our brains. And Ben essentially said that. He actually said, I don't think we will ever find out how a thought is formed because we're made in the image of God. And there's a little joke among neuroscientists. It goes like this. Is the brain smart enough to figure out how it works? And at least Ben says no. Now, I do think when we get to the classroom up there, we could ask that question. And he'll say, I can just imagine he'll say, let me show you. Right? Yeah. An amazing story. And a secularist could say, you're just controlling yourself. But a person who has had that experience will tell you, I couldn't have controlled myself. I am getting help. I'm getting wouldn't you all agree with that mostly? Some of you maybe not be believers in this. I understand that. But, and this is not just ordinary dumb people like you and me folks that say these things. C.S. Lewis, perhaps as bright a man as you'll ever read about in your life. Is that correct? He was an agnostic, an atheist. He became a Christian. And he wrote a book called Mere Christianity. Very, very interesting. So these are not dumb people that are saying, I'm getting some help. This is beyond me. I can't control myself. I couldn't, but it's happening now. And the testimonies are endless. Pastor.
How does that work with, like, addiction recovery? So you have an addiction going on, you have the neural pathways well established in habits. How does that happen where you block those receptors off? In some cases, for example, we're using the understanding of I've been created, or I was crucified
these metaphors we use to try to get a handle on what has happened.
Right. But in some cases, the addiction continues.
Yeah.
How does that...
I have a theory that I'll just share with you. By the way, we have a fairly precise definition of what an addiction is in terms of neurotransmitters and how the body is unable to produce the transmitters by itself, and so this is a true addiction. This kind of thing is pretty well understood. But I used to be a traveling preacher, and my wife and I, and in the early years with our 2 daughters, we sold our home. We had a big trailer we lived in, and we went for 6 weeks to one place, and I would talk every night or most of the nights and so forth. And because I was talking about the Bible and living right, people would often come under conviction about their smoking. And I would go to their home, and they would tell me about that, and I would pray with them and try to teach them. I learned this from Joe Cruz. You've all heard about the 5-day plan to stop smoking? Developed by an Adventist pastor, 60 years ago, and an Adventist physician. Well, Joe Cruz taught me the 5-minute plan to stop smoking. I was never a smoker, but I mean, he taught me. And so I would work with people on that. And my experience with 98%, whatever, for reasons that I'm going to ask in class one day, God still allows those people to struggle greatly in trying to gain that victory. But there's a promise in the Bible, you all know this, most of you know this, that says, God will not let you be tempted beyond what you're able. 1 Corinthians 13. And I would explain that to people, and they would have victory, but it was a battle and a march. That's been my experience. Occasionally, for reasons that I can't explain except that God just said to himself, this person cannot do this, they cannot handle this. And I'll just tell you one story. And he just takes it away. We were in a meeting in Virginia, I think it was, and this lady came to me and she said, would you and the pastor come visit me, please? Which we did. And her husband, she had an impossible situation. I've conducted lots of stop smoking programs. I've helped thousands of people quit smoking. And there are times when we tell people, this is not the time for you to do this. You just had a divorce, you just lost a spouse, or there are these circumstances, it's just too much. It's an overload for people. And her husband had just been imprisoned because of a DWI, and he killed a couple of young girls on the highway. She was in the process of losing their little home. She worked in a dress shop 2 or 3 days a week. I mean, she didn't make enough money to pay the electricity. And she'd had 2 or 3 other problems that I can't now remember that were just enormous. And I was saying to her, I do remember her name, Florence, I'm not sure that this is the time, but she was sure that it was. And so the pastor and I prayed with her. I went through the Bible texts that are sort of promises that you can do this. And we left her home. I'll have to confess my faith was weak on this question. The next night, we visited her that evening. There was no meeting that night, but the next night there was a meeting. And I was getting things ready, and people were coming, and I saw her come in the back door. Way back there was a pretty big auditorium. And I walked around back there and caught up with her and said, Florence, how are you doing? And she said to me, I haven't wanted a cigarette since you were at my house. And by the way, I didn't explain enough how heavy this addiction was. She had been in the hospital for something, another problem she'd had, and you can't smoke in the hospital. So she had quit smoking. But the moment she was out the hospital, she was smoking again. You know, she wanted to. She just, such a drive. And she said to me, well, I haven't wanted a cigarette since you were at my house. And the next night that we went to visit her, before the meeting, met her at the door. How are you doing, Florence? Same story. I haven't wanted a cigarette since you were here. And in my opinion, that woman was in a situation where it was impossible for her personally to suffer through the problem that, for reasons that I don't understand, God usually lets people suffer through. He just took it away from her. I've seen that less than that many times in working with thousands of smokers as a preacher. I used to come home. We always ask the people if they would like us to have their cigarettes because it's very dangerous to keep them around. And I don't want people to think I'm starting to smoke, so I don't put them on the seat. I put them on the dashboard, like, so see, there's nothing to be hit here. I'd come home sometimes after an evening of visiting and packages of cigarettes all over my dashboard. Interesting world.
May I ask you, you're speaking of cigarettes, but what about alcohol or other drugs, methamphetamine, those type of things? My thinking for that certain people can get out of those addictions a lot easier than someone else, and some people may never. My thought has always been that cells are being damaged, and maybe those neurons can't.
Yeah, my daughter's an expert in that field, and she's taught me something I can share with you. If the addiction has been around long enough, the ability for the body to make these, there's a name for it, these euphoric experiences that our bodies do, the enkephalins, and what's the other substance? Most of you would know the name. The endorphins and the enkephalins that are proteins our bodies create, and they are neurotransmitters, and they give us these pleasurable experiences that their body, if they are addicted long enough, never is able to make them again. Her work is working with people who are addicted, and those kind of people have to be on this, at least this is the current scientific opinion, they have to be on methadone or something like that the rest of their life. If it has been less time, and it's not specific, it's probably different for every person, they can wean them off the methadone and their body will come back and start producing those things again. The problem is the pathways. You didn't come here to hear this, so I'll try to close this off, but people who have been smokers, you can get the nicotine out of their body in less than 24 hours. Most people aren't aware of that, but that's in the published literature, and we saw that before it was ever published, just when we were working with people. And so the addiction is no longer because there's nicotine in the body. The addiction is neural pathways, like Ben has talked about. I've had people come back to my class after 10 years of not smoking. And they went out to the shop one time to look for something, and they pushed over a pile of stuff, and there was an old coat that they used to wear 8 years ago or whatever. And they put that coat on, and there was an old beat-up pack of cigarettes in there with 2 cigarettes in it. And they thought, well, that's... And just as a joke almost, they pulled that cigarette out, and all of a sudden, they're addicted just like that. So there's a pathway issue as well as a substance issue. And you all know this. Even though this person finally gets off of the methadone and their own body is making neurotransmitter, that doesn't mean they don't have this longing for that experience still. It is a tough thing, I'll tell you, to see kids get on this, because they're messing their life up for life. It's a horrible tragedy that we have going. I know we need to quit. There was one more hand over here somewhere, was there? Okay, all right. Well, I was going to do one more thing, but it's 5 minutes past, so I'll just wait till tomorrow evening. Tomorrow evening, I'm going to show you this clip. It's not an interview I did of this. It's a very interesting story, a fascinating story, not just because you see the development from a single egg that's just been fertilized, the MRI imaging all the way to birth. Just fabulous. But the thing that is so amazing about this, I'll wait for tomorrow night to tell you. God bless you.